It's my pleasure to introduce today's presenter. So Kevin Steele is a graduate research assistant in the Biological Systems Engineering Department at the University of Nebraska-Lincoln. He works with Dr. Yi Shi, an associate professor and agricultural intelligence engineer in the Agricultural Intelligence Research Lab. Originally from San Diego, California, Kevin received his undergraduate in mechanical engineering from Brigham Young University and is currently pursuing a PhD in biological engineering at University of Nebraska-Lincoln. Kevin's research interests involve plant protection, unmanned aerial systems, or UAS, as you'll hear abbreviated to, with a particular interest in UAS-based spray modeling and experimentation. So I know we're all really excited to hear this presentation here at the Great Lakes Commission. I hope you guys are too, and we're gonna pass it off to Kevin, so please take it away.
Awesome. Thank you, Teresa. Am I unmuted? Can you hear me?
Yes.
Perfect. Let me go ahead and share my slides.
All right, they look good. You're in presentation mode.
Awesome. Thank you for that introduction, Teresa. I'm glad to be able to share a little bit about the research I've been doing here at the University of Nebraska-Lincoln in the Agricultural Intelligence Research Lab. As Teresa mentioned, a little background about me. I got my undergraduate in mechanical engineering, and I don't have any weed science or biological sciences background. And so I know a lot of people in this circle and in these groups have those types of backgrounds. So unfortunately, I won't be able to comment much on the biological principles of Phragmites and some of the other things, but the approach we're using involves a lot of engineering and technology, and so I look forward to sharing some of those technologies today. Just a brief outline of what we're going to talk about today. I do want to note that I understand there's lots of different disciplines involved in the treatment of Phragmites and the management of Phragmites and research. And we all have different technical backgrounds, and so I will try to share the technical expertise I have and some of the technical stuff we're doing in a way that is accessible to all without dumbing it down or speaking down to anyone. As I've said, I have no weed science background, nothing with invasive species or natural resources. We got involved with this. Our lab at the University of Nebraska-Lincoln is involved with agricultural engineering. Our lab has worked heavily with drones and specifically with sensing type drones using multispectral and hyperspectral sensors to detect water pressure, nitrogen pressure, and other types of parameters. But recently we've been interested in drone sprayers as well. And we got involved with the Nebraska Department of Agriculture has several groups involved with invasive weeds and noxious weed management. And we got connected with some of those groups, and those groups use drone sprayers to treat Phragmites. And here's a image, or excuse me, two images here of what the local Phragmites spraying industry calls frag hunting. So what you see here is two different sites that has Phragmites present. The green lines you see here are the flight path of where the drones have flown. And the pilot was told to come to this site and spray Phragmites there. They were told there's Phragmites present. And so they arrived, they took off their drone, and they looked on the remote controller of the drone as they're flying. They were just looking around, looking for where the Phragmites is, hence the name, frag hunting. And obviously this is inefficient, not the best use of their time, but perhaps more concerning and more of interest for research is how this makes it difficult to control Phragmites. For instance, we don't know if all the instances of Phragmites have been sprayed if you're just manually hunting for it on your drone. In addition to spraying a patch multiple times, concerns with that, and other concerns, drone sprayers do have autonomous spray capabilities. However, they are mainly used for agricultural row crop applications or for spot spraying. And so this frag hunting is a common practice, at least here in Nebraska, for if you're using a drone sprayer to spray drones, you do this manually. Some of the concerns outside what I mentioned here are with drone sprayers in general. Spray drift, drift being any time that you apply a chemical, a product through the air and it doesn't end up where you want it. Spray drift occurs with ground-based rigs, with drones, and even with crop dusters. However, there's been decades of research on ground-based drift as well, ground-based rig drift, as well as crop duster or manned aerial drift. However, very little research and time has been spent on the drift from unmanned aerial systems, UAS or UAV. I'll call them drones throughout this presentation for simplicity. You can see two images here of drones being used to spray. The image on the left is a single rotor helicopter, and you can see it creates some pretty interesting patterns in the spray. And obviously, it's not just going straight down to the crops. Lots of complicated fluid dynamic interactions are at play there. And perhaps even more common on the right here is you see the spray not going directly underneath the drone, but drifting off to the side, likely due to wind or other motion. And this is a concern when you're using a drone to spray anything, whether it be Phragmites or another weed or applying any sort of product. And so this is another consideration as we drone spraying in Phragmites applications matures, is how can we use drone sprayers responsibly to treat these crops? And I'll touch a little later in the presentation about how our group is approaching this problem. Now, if you want to use a drone sprayer to spray Phragmites and you don't want to do the colloquial frag hunting, and you want to use a more autonomous, non-manual approach, there is a way to do that. I'll show you the workflow here. You have to use a drone, a camera drone, to go acquire imagery of where your Phragmites is. So you'll put a little drone up in the air, take a lot of images. You'll then take it back to the office and upload it to software where you can stitch the images together into a mosaic. Then you have a big picture showing the entire area you just surveyed. And you can either create a vegetation index map that's popularly done in agriculture applications, or more pertinent perhaps to Phragmites is you can manually identify the locations where the Phragmites might be and draw boxes around them. You can then use those to create a prescription map that can be uploaded to a drone sprayer, a separate drone. Note that the imaging and the spraying drones are separate here. And then you upload that prescription map to the spraying drone and execute your mission. And this process is being done right now. It is rather clunky and it's not very popular. Most people do manual spraying. And this involves multiple drones going back to a desktop computer, different software packages, and is not convenient and not helpful for improving autonomous spraying. Our group, the Air Lab at UNO, is hoping to develop, and I'll show you our efforts to develop a sense and spray type system. This flowchart shows that a drone will be able to sense where a weed might be, the primary sensor being a camera. So it'll have a camera on board that will take a picture. It will then use this picture to calculate if there's a weed present or not. Then that calculation will determine if there are Phragmites there or not. If there is Phragmites there, the drone will adjust certain parameters, such as the flight height, the flow rate, the location of the drone, and then it will spray. And then it will once again take another picture, calculate if there's a weed present, adjust parameters, and spray. And this is all done autonomously aboard one single drone. And you can see here there's additional steps required to do some of these calculation steps. This calculation and determining of is there Phragmites present is a major component of this presentation, a lot of what I'll talk about. But understanding the context of why we want to build a Phragmites detection model is important as it drives a lot of the design decisions that we've made. We want our drone to have a computer on board that can, in near real time, take a picture, run its detection model, and then spray and continue in this flow. And so there are certain steps required to collect data, annotate, and then train your model. But we are hoping to develop a sense and spray type system. I will note that there are applications very similar to this in agriculture. Particularly a famous example is John Deere's See and Spray, which is a ground-based spraying rig. And you drive it through your row crop field, and it has cameras on board, and it'll take a picture and spray if it sees weeds, following a similar flow chart as ours. However, there are extra considerations when you're using a drone that we have to take into consideration. So with this being our end goal in mind, I'll talk a little bit more about our specific project and some of the Phragmites type questions and interests that we have. Just a brief background about our project, working with, as I've said, the Nebraska Department of Agriculture and some of their noxious weed groups, which some of them are on a county level, others are natural resource district level. We're working on a 4-year project to build an accurate detection model, integrate this detection model onto a computer aboard the drone, and then perform conditional operations, namely spraying. We are currently in the first year of this project. We're currently in the building of the detection model phase. And so we don't have a completed detection model right now. We unfortunately don't have results from that model to discuss today, but I do have some interesting topics to discuss regarding the architecture of our model, as well as some of the additional considerations that we have. A word on the edge device we're using. As I've said, we're going to have a computer on board our drone to run our AI detection model, and the computer we call is an edge device. And I know the term edge device has specific meanings within computer networking groups. I'm not using that definition. I'm using it as a way to say it's a standalone computer on our drone that is controlling the drone as well as running an AI detection algorithm in the background. And so we're using an NVIDIA Jetson Nano, which you can see here. This can fit in your hand. It's a fairly small model. However, it is optimized to run, it's optimized to be able to run fast AI models. In particular, the GPU is set up in order to be able to handle that. This right here is a picture of one of the drones we have been using. This is a DJI M100 drone, which is now a discontinued model, I think. But we can use this model. It's built to be able to be customized so that we can use our own onboard computer and control the drone using that computer. So this drone right here, I can take off and fly using a controller. In addition, I can also write some code, upload to this onboard computer, and fly it using that. And that's important because we want to be able to run our weed detection aboard the drone in near real time in order to detect and spray Phragmites. This drone is quite small. Obviously, we won't be using this for spraying. We're using a larger model, a DJI M600. However, this is a good proof of concept for us, and we've used this extensively to do testing with the Jetson Nano as an edge device. I'll talk briefly now just about review of different weed detection models. And I'm primarily going to be talking about detection models, AI detection models that have been used for invasive weeds, specifically Phragmites detection, and also specifically using UAS or drone imagery. I focus additionally on the use of neural networks. However, as you'll see, there's a wide variety of AI models that have been used, and I'll discuss some of the intricacies of those. As I mentioned before, weed detection models are nothing new. They have gained quite a bit of traction in the agricultural fields. However, they haven't quite transitioned to the natural resources or invasive species type work. And so we're hoping to take some of our experience in our group with agricultural type models and use them to leverage them to be able to perform tests with invasive species and other similar applications. There is limited research out there on using these models with drones for Phragmites detection. There are groups out there that do this, however, there's not many of them. Some of them, interestingly, have found some success using multispectral and hyperspectral imagery, and they've shown moderate accuracy and some high accuracy doing that. There is, as I mentioned, a wide variety of models investigated, and there's yet to be a real true cohesion of consensus on which model is best. And finally, a real-time detection with a model deployed aboard a drone is still a work in progress. There is no, there is no product out in the market today that you can buy to have a drone go spray your Phragmites for you. It'll do detection. That does not exist. And that is something we're specifically wanting to work on, to be able to deploy our weed detection model in near real time aboard a single drone. I'll just mention briefly some of the different algorithms that varying groups have used with a support vector machine, random forest, maximum likelihood classifier. For those familiar with machine learning and AI algorithms, these are quite popular algorithms and have shown good success for image classification, object detection. And of course, neural networks, a very hot word in lots of fields these days. And there's lots of different types of neural networks. We ended up deciding to use a convolutional neural network. However, there are many different varieties. As I said before, there is research out there for all of these different types of AI algorithms. However, there's yet to be true consensus on which one performs best to detect Phragmites. And some groups have compared these. However, there is no scientific consensus out there yet. The reason our group decided to use convolutional neural networks, there's two main reasons. One, the structure of a convolutional neural network and neural networks in general has been shown to perform quite well doing object detection with images. And a second and perhaps more important reason is we've found success in our group using convolutional neural networks with weed detection in agriculture and other projects that we've done. And leveraging those results and some of those experiences, we felt that we could have the most success using a convolutional neural network in this project. And just a brief high-level overview of some of the basics of a convolutional neural network. And I apologize for those who are familiar with this already. The basics are you have pixels in your image and you perform a convolution operation on those, and the weights of the convolution are selected by your model to best optimize the convolutional operation to detect objects and do classification. And you perform this convolution operation a number of times with different strides and different parameters. And then you can feed this into a neural network where a neuron can input the weights and other parameters give you outputs to keep feeding your neural network forward. I'll now share very briefly the proposed structure of our neural network. Our proposed architecture. We have proposed 5 convolutional layers and then 2 fully connected layers. And each of the convolutional layers also have max pooling technique that has been shown to improve the accuracy. So we have a total of 7 hidden layers, an input layer and output layer, and 2 of those hidden layers are fully connected, which is a traditional neural network kind of nested within a convolutional neural network that has been shown to improve accuracy. A word on the justification for this. There is no perfect way to optimize the architecture of a neural network, and there's been lots of research papers, not just within lead detection, but within neural network circles in general, of how to select an architecture. And the consensus is to identify an architecture that has performed well in a similar problem, and then start with that architecture and use a similar architecture to try to address your problem. There's a number of hyperparameters that can be adjusted as well in this. And so we looked at several existing architectures, some from literature and other industry standard architectures, and we felt comfortable with something similar to the architecture I just showed you to be able to perform well in the Phragmites detection problem. So the way we go about collecting our data, we use this drone right here. It's a DJI Mavic 3 multispectral. It's got a RGB camera and then 4 multispectral sensors, a red, green, near infrared, and red edge band. I will say we are collecting data with the 4 multispectral sensors in all 4 bands. However, we're not going to be using this data initially to train our neural network. Initially, we are just going to be using RGB cameras in order to do the Phragmites detection. Several reasons for this is that when we use an RGB camera, we can use images from other types of drones that do not have the same bands as, excuse me, that we can use drones that don't have multispectral sensors, and so we can use those cameras to collect data. So we'll go to a field. This is a field that we flew in Lincoln last year here in Nebraska, and we'll fly very high level. This one I think is between 100 and 200 feet above, and we'll take hundreds of pictures and we'll stitch these images together into an orthomosaic. So we have one image here, and we'll zoom in and we look and say these may be Phragmites. We identify several locations that could contain Phragmites, and then we'll take our drone, bring it closer, and collect higher resolution data closer to the surface, and also not bird's eye view. This is a directly above imagery. The camera's pointing straight down. We collected data afterwards using off nadir, where the camera's not looking straight down, to better mimic the situation of the drone we eventually want to use. And I'll excuse me, I'll show later some of those considerations. In addition to flying our own drone and collecting our own imagery, we also are trying to collaborate with local service providers here in Nebraska to collect Phragmites pictures and data around the state in order to build a robust model. One of the important considerations when building a detection model, a Phragmites detection model, is to not collect data that all looks the same. You need a wide variety of lighting, of angles, of altitudes. This is a picture that a local service provider took when they were doing work at a public site for a local weed control authority. And so we're working actively with these weed control authorities. And some of these weed control authorities also have their own drones, and they take their own pictures of Phragmites, and we can also use those images to train our AI detection model. And so we're hoping to develop relationships with the weed control authorities in addition to the service providers to understand the whole range of possibilities. Another important consideration to improve the robustness of our model is to make sure we are considering the Phragmites through all seasonal changes. If there's snow on the ground, how could that impact the ability of our AI detection model to be able to perform? We want our model to be able to perform in a wide variety of conditions. And so we're attempting to collect data throughout all seasons and life stages of Phragmites. This is a little difficult given the timeline of our project. We started just in September, October of this past year working on it. So it takes time to collect data across all seasons. And this is one of the reasons that our model still hasn't been finished yet. But we're hoping to include all these diverse data points in order to improve the robustness and the accuracy of our detection model. After we collect the data, we then process and annotate it, and that typically just involves uploading our data to software that allows you to draw a bounding box around the Phragmites, and then we can use that image and the associated data to train and validate our detection model. Just a word on the how we foresee our detection model working, some of the geometry involved. As I said, the drone is not going to be taking pictures directly beneath it when it is flying and when it's working on its detection model algorithms. It's going to be looking forward, taking a picture, and deciding to distract Phragmites in front of it as it's flying towards that patch. And so we tried to get some estimates of what some of these numbers might need to be, so we can optimize the angle at which we're taking the pictures, so we can collect a lot of our data at the angle where we would likely be doing our detection. So some of the variables to consider here are flight altitude. Drone sprayers are typically flown anywhere from 10 to 15 feet above the crop canopy. That's both in agriculture and in Phragmites spraying or other invasive species spraying. And so if you're flying 10 to 15 feet above the crop canopy, that can be, depending on the height of the Phragmites, can vary widely. And so that's one of the considerations is flight altitude. The detection distance, how far ahead the drone is looking and taking a picture and then deciding if there's Phragmites, is determined by the flight speed, which we estimate at a pretty conservative and typical speed of around 10 miles an hour, somewhere in the ballpark of 5 meters per second. And then this can lead to a detection distance of somewhere between 3 and 4 meters, close to 10 feet in front. And that's also a function of the inference time, which is how long it takes for the AI detection model, once it's taken a picture, how long it takes for it to run through the algorithm and determine if the picture contains Phragmites or not. Typically, this can be if you set it up right and you correctly set the software up in the set up the code in the edge device. The inference time can be less than a second. We're hoping to get it down to less than half a second, which is very doable. And then so the detection distance is a function of this inference time as well as the flight speed, also actuation time, which is simply a variable to include both the time that it takes to turn on the pump, whether that's by activating a switch, a relay of some sort, of transistor, and so sending a signal to turn on the pump, and then also to leave the pump on long enough to spray the whole patch of Phragmites. From all these, we can back out detection distance of anywhere from 3 to 4 meters, and our angle that we're looking down to see the Phragmites ahead of us, something in the ballpark of 50 degrees down from the horizon. So we use these to optimize how we're collecting our data in order to build the most accurate and robust detection model. Briefly on some of the challenges that we know exist out there with Phragmites detection models. Namely, there's the dead versus live Phragmites and also native versus non-native. These are concerns. Obviously, we don't want to go and spray a patch of Phragmites that's already been sprayed, that's already been dealt with. And so the best way to deal with this is to train our model to include other classes. So when you take a picture to say, is there Phragmites or not Phragmites? Instead of that approach, to say, is there live Phragmites, dead Phragmites, or no Phragmites? And the way we go about by doing that is by collecting more data involving both patches of dead and live Phragmites, and then training the model accordingly. Similar approach for native versus non-native. Take pictures of both, and then train the model accordingly. Both of these approaches have been shown to work quite well, and there are groups who have trained models to do both dead and live Phragmites as well as native, non-native. However, the consideration here is what's the consequence of spraying dead and live Phragmites, native versus non-native, or the consequence of missing a patch because it misidentifies, and those are all considerations that have to be taken into account. We understand that these are challenges, although we're not yet pursuing these challenges. We're focused on building our preliminary model in order to detect Phragmites, and then we'll eventually investigate some of these challenges. over. Very briefly, I'll end just on some of the future work that we hope to do. Obviously, to continue and finish our Phragmites detection model, have some results that we can then share about our accuracies. But also, we're very interested in the spray efficacy and some of the modeling of the spraying, some of the dynamics, the interplay between the wind and the downwash propellers. When you're using a drone sprayer to spray Phragmites, is it actually applying to the crop, or excuse me, to the plant? Is it actually ending up where you need it to? We've done some preliminary work, as you can see here, with some computational models, physics-based fluid dynamic models to model some of these sprays to improve the efficiency, efficacy of spraying to make sure that these drone sprayers work. And then finally, as we go about designing our sprayer drone, this is an earlier prototype of our sprayer drone. This is the DJI M600, a bigger drone. You can see it's got a little tank there strapped on. As we design this to be a drone sprayer, being intentional and designed such that we work with the end users, both those who are out there spraying, as well as those interested in the research and other considerations, to ensure a responsible design so that it does the best job at spraying and treating Phragmites. Just want to give a couple acknowledgements to the different groups that have been involved in my research, the Lower Platte Weed Management Area, and then from Lancaster and Douglas County, those in my group and others that support. And there's a couple references for those interested. I think that's all I have. Thank you.
It was absolutely fantastic. And I learned a lot. So let me put up this little screen. So I put Kevin's email up here. So obviously we now have time for Q&A if you have questions, but also if you're like, I don't know, later today or next week, you have thoughts and want to know more information, there's how you can get in contact with him. But yes, oh my gosh, great presentation. And I think we can all say like how this is going to be awesome when this is, you know, a few years down the line, and so appreciative that groups like you and your colleagues are working on something like this. Okay, guys, so if you have questions, please put them in the Q&A function. Check the chat. Okay, so from Julia, how small of a patch do you think this model would be able to detect?
Yeah, that's a good question. A lot of it comes down to the spatial resolution of the imagery being used. Now, if we're flying at an altitude of, say, 20 feet above the crop height, we're looking somewhere in the ballpark of a pixel being 0.1 inches wide, 0.1 inches tall. And there are rules of thumb out there about how many pixels you need in order to detect something at all, and anywhere from 3 to 10 pixels, you can do some sort of object detection. And so I suspect that if you're flying 20 feet above the crop height, you have 0.1 inches per pixel, then you'll be able to detect a patch of Phragmites that's just a couple inches wide, up to anything bigger than that. But once again, that depends a lot on the specs of the camera being used aboard your drone.
That's awesome. In the future, how much, I know there's different drones that hold different volumes. This question's from Nicole. How much volume of herbicide could these drones potentially hold?
Yeah, the big concern with that is the battery life of drones. Commercial drones these days that are meant for volume spraying, so spraying a lot, the biggest models are something like 10 gallons, and they can fly for about 10 minutes.
Wow.
10 gallons. Then you need to land them and put new batteries in. And so we would be going, I think putting a ton of volume in your drone is not going to be able to optimize our specific use case, considering that we have a lot of time of flying and looking for where the Phragmites is present. And so our initial model is we're keeping it to about a gallon or less, just to that's our initial prototype to see how it works, and then we'll scale up from there. The big concern is battery life, and that's just an industry-wide problem that you can't get much better with a fully loaded tank than about 10 minutes in the air.
From Sam, how do you prevent overspray from getting on the camera lens and impacting image quality?
Yeah, great question.
That a problem?
Yeah, it's not a huge problem, although it's not a very well understood phenomena. The camera, wherever you put it on your drone, there is a significant downforce from the propellers. Typically, these drones have 4 to 8 propellers, and that provides significant wind pushing the droplets down. And so there's not a huge problem actually with the camera getting fouled up. Typically, if you just wipe it off using the commercial sprayers these days, you just wipe it off every couple of times you fly it. It's just not a problem because of that downwash. However, that downwash is not well understood how the dynamics interact.
Thank you. From Colin, can you use real-time height information? So something from photogrammetry? I don't know what that word is, maybe you do, or LiDAR to help differentiate Phragmites from other species. My drone mapping work has showed that this is helpful, and they are citing the work Brooks et al. 2021.
Yeah, sorry, can you repeat the first half of that question?
Yes. Can you use real-time height information from photogrammetry or LiDAR to help differentiate Phragmites from other species?
Yeah.
And Colin, if you're on, I can unmute you if you want to like re-give your question, and if I'm just butchering it. So
I will say I know that there has been work on that. I haven't personally used any sort of LiDAR real-time altitude technology. We've done most of ours based off of computer vision type principles. However, that is an interesting approach that certainly I imagine would bear good results.
okay. Roll through. From Tommy, how big of an area can you cover both mapping and spraying?
How big of an area can you cover mapping and spraying? That's once again, it comes down to your flight time and your flight speeds. And, off the top of my head, the commercial sprayers right now that spray in agricultural fields, but they have a similar payload to what our drone will have. They can do on the order of one to a couple 50 to 100 on the high end acres per hour. I think that's pretty optimistic, and so I'd say with our drone, we're looking at the 20 acre per hour if you're in the air for most of that time. That being said,
that's a lot. Yeah.
That being said, it's quite variable on a lot of different parameters there.
From Joshua, what sort of biological/ecological information do you guys need to help this project succeed?
Yeah, that's a great question. As I mentioned at the beginning, I lack any sort of biological training. I think one of our questions is involving the multispectral, hyperspectral imagery about how that interacts with the. I've done reading and stuff regarding general plant matter and how that interacts with the multispectral, hyperspectral imagery, but specifically, I'd be interested to know how that interacts with Phragmites, and maybe that's not a biological type question, but that's an interest of mine that could assist.
That's awesome. Yeah, I'm sure there's going to be a lot in the future once this is more well developed. But
right.
From Julia, what parameters/characteristics would you key on to distinguish native from invasive Phragmites once you guys maybe eventually get to that step?
Yeah.
Again, I know you're not a plant person, so.
Right. Yeah. Once again, and that's part of the thing is when you use a a AI detection, a convolutional neural network. They're sometimes colloquially called black boxes because you load your training images into these sets and it runs mathematical operations, but you don't know what it's looking for. Sometimes you have to back it out and just see what it's looking for. And so I don't know, even for live non-native Phragmites versus just graphs, what the model's doing isn't something that we actually input. It looks for what the differences are, and then the model itself decides what kind of detection parameters to use there. We just upload the images with boxes around where the Phragmites is present.
Yeah, that would definitely be interesting because obviously they're so similar. So, you know,
right, yeah, very difficult problem.
True detection is even possible, but wow, that'll be really interesting. Right. How long until this technology is available to managers? Of course, that's what people want to know. Your best estimate.
Yeah, as I said, a lot of this technology is, well, all this technology exists, and a lot of it's used quite well in agriculture right now. And so the question is how long will it take kind of to shift over to a more invasive species management. And I don't have a good intuition about that. That's more of an industry type question. I hope in the next 5 to 10 years, this sort of technology would be mature enough to enter these type of fields.
That's awesome, I'm sure. Yeah, I can, by the questions here, I can already tell people are very eager to see something like this. Okay, just scrolling through. There's so many Q&A questions. Have you come across any research that indicates it is possible to distinguish native versus invasive Phragmites using RGP?
Yeah, I think I have, although I don't have that reference on me right now. I'd have to do some digging to see if
that's a good enough answer.
Remembering that wrong or not. I'm sorry, I don't have a better answer for that.
No, perfectly fine. If anyone, I guess, knows, please put that in the chat. If you're listening to this and you're like, oh, I know that, maybe share it out with everybody. This is from Mark. Giving limited drone flight times when loaded, might it be more efficient to map the frag locations first and then go back and then spray?
Right, certainly that's a great point there. And lots of people have had similar questions and concerns. What's the point of putting it on one drone if you can get such low flight times? And for that reason, that's one of the main reasons that this sort of technology hasn't quite caught on, because of the inherent struggles with battery life. One of the reasons we're pursuing it is because it's of academic and research interest, but we also think that the advances with battery technologies and other types of technologies to advance this will eventually make it more practical. That being said, it certainly right now is much more practical to fly a mapping mission and a spraying mission.
Yeah, maybe in like the 5 to 10 years when this is like commercially available, the battery life will also be a lot better, and that won't really be an issue. So yeah. From Julia, given that a lot of, sorry, these are, I hope you have time for these questions. Okay.
No, it's fine.
Given that a lot of frag treatment is grant funded, at least in some regions, and those grants are federal, which so far prohibits the use of drones with Chinese parts, will your drone avoid something like that for commercial that's applicators?
Yeah. Yeah, because we're state funded right now, it's not a huge concern of ours. Obviously, lots and lots of rhetoric out there about this. We have had extensive discussions. Right now, we're a DJI-based system, which is obviously a Chinese drone brand, and they're the biggest drone brand in the world. For the technological advantage that DJI has right now, it's significantly better to use their products and makes it significantly easier to build an effective drone system. Whereas American made parts and products, unfortunately, as of right now, just haven't matured enough in order to do that. So kind of a roundabout way to answer that question. We have talked about it. We're using DJI because they're significantly better from some of the technical standpoints. And we just hope that some of these issues will be resolved. And if not, we'll figure out what to do.
Yeah. Again, maybe in a few years it will catch up and That won't be
Yeah.
won't be an issue.
Certainly possible.
From Grace, would this detection system be best set up for detecting and spraying large patches of Phragmites, or do you see this possibility of a system to be able to complete follow-up or spot spraying that is often needed after initial treatments?
Yeah, I think when people hear about drone spraying, their first, at least in the agricultural communities I work with primarily, their first thoughts are spot spraying, because spraying a large area with a small drone doesn't make sense all the time. And so I think that it would have perhaps better application in a follow-up. But the in agriculture, which is kind of a couple years ahead of the natural resources and invasive species type applications, in agriculture, full field volume applications are gaining traction, and so hopefully the drone technology will follow. But as of right now, the spot spraying is certainly a more viable use.
Okay. Nicole, have I missed any? I'm scrolling through the Q&A. Do you see any that I've missed?
No, I think you got them all. Those are all really good questions.
Those were fantastic questions. Wow. Like I said, on the screen is Kevin's email, so I already asked him it's okay if you guys email him with questions after. I want to thank you. Let me just check the Q&A one more time to see if there's anything else. Okay, it looks like we have them all. So I already know we've gotten questions about if this is being recorded, and it is, and I will process the recording and it will be emailed all to the registrant so you guys can share it out if you had to leave early, you want to catch it. It will be available within the week, and it's also posted on our website. So just keep your eyes and ears peeled, and I will be sending that to you guys. Yeah, and I just want to thank you guys for watching. This was a fantastic update, really. So thank you so much, Kevin, and thank you guys all for being interested in the topic as always. And have a great afternoon.